Hello. Today I'm going to talk about refined list coloring of graphs. We start with the famous four-color theorem, which says that every planar graph is four-colorable. However, Freud proved that there are planar graphs that are not four-choosable, although every planar graph is five-choosable, as proved by Thomason. The questions I'm interested in is that how far can a planar graph from being four-choosable? Is it true that every planar graph is almost four-choosable, or there are some planar graphs that are barely five-choosable? Well, then what you mean by almost four-choosable or barely five-choosable? For that questions to be meaningful, we need a measure of the distance of a graph from being four-choosable. Right? We need a measure. In this talk, we'll introduce a few such measures. The first measure is as follows. For what subgraphs h of g, g minus EH is four-choosable. The sparser is the subgraph h, the closer g is from being four-choosable. Right? So in particular, we can ask, is it true that every planar graph has a margin m such that g minus m is four-choosable? Or even every planar graph has an induced margin m such that g minus m is four-choosable? The next refinement is to ask how many vertices really need five permissible colors. We say a subset of vertices is four sufficient if for every list assignment L, which assigns four colors to vertices in X and assigns five colors to everybody else, every other vertex, G is L colorable. The fewer vertices need five colors, the closer is the graph from being four-choosable. We define a graph to be, we say a graph is 4 plus epsilon choosable, 4 plus epsilon choosable, if every subgraph H of G has a four sufficient subset such that X is at least this big. That means at most the epsilon fraction, an epsilon fraction of vertices needs five colors. The remaining vertices need only four colors. Now, by this definition, then we ask what is the smallest epsilon such that every planar graph is 4 plus epsilon choosable. Okay. The third refinement is go to a multiple coloring. A bifold coloring of G is to assign to each vertex a set of B colors so that the adjacent vertices get disjoint color set. So like this graph, and this is a twofold coloring of this graph. Each vertex gets two colors and the adjacent vertices get disjoint color sets. Okay. For the third refinement of list coloring, we go to multiple coloring, where bifold coloring of a graph is assigned to each vertex a set of B colors, so that adjacent vertices receive disjoint color sets. Now, we say a graph is AB choosable if G has a bifold L coloring for every A assignment L. So this bifold L coloring, that means each vertex get B colors from its list. Okay. Now, we say graph G is fractional R choosable if G is AB choosable for some AB for which A over B is less or equal to R. It was proved by Harlan, Tooth, and Freud that the fractional R choosable is equivalent to fractional R colorable. Of course, AB choosable is not equivalent to AB colorable, but fractional R choosable is equivalent to fractional R colorable. This implies that every planar graph is fractional four-choosable. Right? So this kind of multiple coloring, multiple list coloring, does not introduce a new parameter. The fractional choice number is the same as the fractional chromatic number. To make a refinement of list coloring by go to multiple coloring, we introduce a new concept which we call it strongly fractional R choosable. So G is strongly fractional R choosable if G is AB choosable not for some AB but for every AB for which A over B is greater or equal to R. Then we define the strong fractional choice number of G to be the infimum of those R such that G is strongly fractional R choosable. Okay, then what it means when we say the strong fractional choice number of a graph is less or equal to 4? It's equivalent to say that G is strongly fractional 4 plus epsilon choosable for every epsilon greater than 0. In this case, you take the infimum of this is R. You take the infimum of those R, you get 4. You get 4. Now, this is the same as saying that G is 4B plus 1 B choosable for every B. And that means G is 5-1 choosable, G is 9-2 choosable, and G is 13-3 choosable, and so on. Okay. Now, we denote by sigma the family of planar graphs, and we define this chi f star sigma to be the supremum of the strong fractional choice number of planar graphs. The question is then, what is the value of this? What is the supremum of the strong fractional choice number of planar graphs? It follows from Alan 2004's result that for every planar graph G, there's an integer b such that G is 4b choosable. But we can ask, is there integer b such that every planar graph is 4b choosable? So here this b depends on G. Can we find a b that's independent of G? Another more interesting question is that whether every planar graph is 9-2 choosable. So in general, so what is the infimum of those epsilon for which every planar graph G is AB choosable for every A over B greater or equal to 4 plus epsilon? So this is same thing as to define the supremum of the strong fractional choice number of planar graphs. Okay, the fourth refinement is to go to restricted list assignments. Okay, so let's interpret four-color theorem in a different way. The four-color theorem says that G is, if L is a four-list assignment of a planar graph G, then G is L colorable, provided that for any two vertices of G, they go to the same list, which means that all the vertices of G have the same lists, Okay, they've got the same four colors. This means four colorable. Right? And so this is a restriction on the list assignment, right? So we're talking about restrict list assignment. So this is a restriction, but this restriction is too restrictive. We want something to be restrictive, but not so restrictive. We need some freedom, but not complete freedom. The restricted freedom. Okay, so then what kind of restriction can we talk about? So assume this lambda is a partition of K, which means that Ki are positive integers and they sum up to K. Lambda list assignment is a K list assignment L such that the color set, the colors used in all the lists is partitioned into Q sets of colors. This is disjoint union of color sets, so that for each vertex V, LV has Ki colors from Ci. Okay? So LV is a set of K colors, but it takes Ki colors from Ci. Okay, so this so LV takes K1 colors from C1, K2 colors from C2, and KQ colors from CQ. So such a K list assignment is called an lambda list assignment. And we say graph G is lambda choosable if it is L colorable for any lambda list assignment L. Okay, so let's look at some special partitions of K. If the partition is this one, if this is O lambda, then lambda choosable is the same as k choosable, right? It follows from the definition. And the non-extreme of partition is the partition k into k copies of 1. Then this lambda choosable is equivalent to k colorable. Okay, so the list, each vertex get k colors, but the colors are partitioned into k parts, k color sets. So each vertex take one color from each of the part. That is the same thing. That is equivalent. So to the case that all the vertices got the same list. Okay, so this is lambda choosable is k colorable. Okay, so this lambda choosability put this k choosable and k colorable in the same framework. Okay, and it follows from the definition that if lambda 1 is a refinement of lambda 2, then lambda 2 choosable implies lambda 1 choosable. Okay, as any partition lambda of k, lambda is a refinement of this partition, and this partition is a refinement of lambda. So therefore, we have the following implication: k choosable implies lambda choosable for any partition lambda of k, and any lambda choosable for any lambda partition of k implies k colorable. Okay. So now we go to planar graphs, and we're interested in 4 coloring. Right? So what are the partitions of 4? So these are the partitions of 4. And the 4-color theorem says that every planar graph is 1, 1, 1, 1 choosable, and the Voigt theorem says that some planar graphs are not these 4 choosable. How about the other partitions of 4? So let's make an interpretation of 2, 2 choosable. What it means by graph is 2, 2 choosable. 2, 2 choosable means that for any list assignment, for list assignment G, L, if L contains 2 positive integers and 2 negative integers for each vertex V, then G is L colorable. So the color sets are integers, and it's partitioned into 2 parts: positive integers, negative integers. So each vertex takes 2 colors from the positive side and 2 colors from the negative side. Then G is L colorable. If this is true, then we say the graph is 2, 2 choosable. Okay, so 4 choosable implies 2, 2 choosable, but the converse is not true. 2, 2 choosable does not imply 4 choosable. Okay, so the 5th refinement of this coloring is we go to restricted DP coloring. First, we define DP coloring, which is a concept introduced by Dvorak and Postel, which is a generalization of list coloring. Let's start with list coloring. So this is a graph, and this is a 2-list assignment. And for such a 2-list assignment, an L coloring of this graph is to choose 1 color for each vertex from its list, so that adjacent vertices get distinct colors. That means if this color is chosen for this vertex, this color cannot be chosen for this vertex. So instead of saying that they cannot get the same color, I say this color pair is forbidden to be assigned to the corresponding vertices. Okay. So then I don't need the names of the colors, right? So the names of the color are not important, and they can cover the names. I just say these 2 colors cannot be chosen simultaneously, one for this and one for that. Okay, so of course this is the same as list coloring, but this kind of restriction do not need to come from the list assignment. Say, I just need to have each vertex a set of colors given to it's a list for this vertex, and there's a list for this vertex. I just put a margin between this set of colors and this set of colors. That margin tells us which pairs of colors are forbidden to be signed simultaneously for the corresponding vertices of G. Okay, that is called correspondence current by Dvorak and Postel, and then it's called by dp current by Sasha Kostochka. And so this is the dp current we're talking about. And we can still give names to these colors, but the names are not important. For example, we can give each vertex the same set of colors, 1, 2, and but the rules is different from this current. The rules is governed by this matching. Okay? And the matching also do not need to come from a list assignment. It can be an arbitrary matching. For example, we can put an H here, and that's provided that it's matching between this color set and this color set. That is the definition of dp current. Okay, so dp can be defined as follows. Assume D's orientation of G and sigma is assignment of arcs. It's a mapping which assigns to each arc a permutation of sk, a permutation of this set. Okay, and then a k current of this graph is proper for this pair. This is orientation together with assignment of permutations. If for every edge E of this directed graph, the color signed to Y is different from the image of the color signed to X under the permutation sigma E. Okay. So this is a variation of proper current, right? Proper current says to end vertex, the end vertex should get distinct colors, but this now you don't have to be the same color, just assigned to one color that you cannot be. So this color pair that cannot be assigned simultaneous to X and Y. Okay, we say graph G is dp colorable if any orientation D and any assignment of permutations to the edges of D, there is a proper k current of D sigma. Okay, so in the original definition, so if sigma is like this, then sigma, each vertex get k colors, and this sigma is matching between. For every edge, it defines matching between the k colors and this k colors of X and k colors for Y. There's a matching between the k colors for these two vertices. And because sigma is a permutation, that means this matching is perfect. Okay, but actually you don't need to be perfect. In the original definition of dp current, so sigma can be chosen to be say a partial permutation. You don't have to be full, not a perfect match. Just match is good enough. But you define this dpk colorable. This is equivalent. Okay, so as we have seen, that dpk colorable implies k choosable. Of course, the converse is not true. For example, this C4 is 2 choosable, but not dp2 colorable. With this kind of assignment of permutations, you cannot color it. Okay. So this is a dp current. Now, for the refinement of this current, we say we're going to talk about restricted dpk current. What does that mean? So this means that we choose a subset of permutations. Okay, and in dp current, so this is assigns to each arc a permutation, but now we want to assign to not arbitrary permutation, but permutations chosen from the set S. So S put the restriction of what kind of permutations you can assign to the arcs of D. Okay, so this is called restricted dp current. Right? Okay, now let's look at some special S. So if S is identity, okay, what does that mean? Then this is the same thing as k colorable, right? This is just every edge, the permutation is identity. That means sk colorable means k colorable vertices, adjacent vertices get distinct colors. Okay. And what is if S equals SK? That's any permutation is allowed. This is dpk current, right? And what about if S is the a group generated by this permutation. So it's the cyclic group generated by this permutation. And this is ZK colorable. This is a concept called the group coloring, introduced by J.J. Ninia Panyantasi, and it has been studied a lot in the literature. Now, what about the case that S is identity? S consists of two permutations, identity, and 1, 2, 3, 4. So this means interchange the color 1, 2, interchange the color 3, 4. Okay. So then, what is S for colorable? Okay. This is signed for colorable. This is the same as the signed for colorable. The signed for colorable, signed K coloring was first studied by Zasnowski, and he studied signed graph coloring in the 1980s. In the Masayava, Raspod, and Sukovria, they studied this concept again in 2016, and they modified the. They used the same definition of signed coloring, but they defined the signed Chromach number a little bit different from Zasnowski, and we adopt that definition of signed Chromach number. Okay, then what is if S consists of two permutations as ID and 1, 2, and then what is S4 colorable? This is this concept which we call signed Z4 colorable. This is a concept introduced by Canon Stephen. We go to more details about signed coloring. So signed coloring. So what is a signed graph? Signed graph is just a pair, G is a graph, and a sigma sign to each edge a sign, which is either positive or negative. Okay, and for coloring of this signed graph, use four colors, 1, -1, 2, and -2, such that fx is different from fy times the sign of this edge. Okay, so z for coloring is defined in the same way, but this negative, so the color set is different. The colors, this is 1, -1, 2, and -2. This is 0, 1, 2, 3, z4, element of z4. So the requirement is the same, but this minus sign means in Z4. Okay, so let's look at what the color restrictions for coloring in this signed graph. Okay, so we use the notation of this matching. Say what it means by for coloring. So if this is a positive edge, then these are the forbidden pairs. So 1, 1 is forbidden to be assigned to xy simultaneously. Okay, so -1, -1, that's forbidden. Okay, and so on. So this is identity. This permutation is identity for this edge, and this is a negative. If this is a negative edge, this is the forbidden pair. So if x is colored by 1, y cannot be colored by -1, and so on. Okay, this is the we can change the name of the color as follows. Then this is identity, and this is 1, 2, 3, 4. That's the permutation. Okay. So now, what is Z4 coloring? Z4 coloring, the positive edge is the same thing. So they cannot be colored by the same color. And negative edge is by negative sign. So 0. The -0 is 0. -2 is 2. But -1 is 3, and -3 is 1. Okay. So if you change the names of the color, is 1, 2, 3. Then this is the permutation identity. This is the permutation 3, 4. Of course, it's equivalent to 1, 2 if we can change the name of the color. Okay, so under this definition, then a natural question is for which subset S of S4 every planar graph is S4 colorable. As we said, we're interested in planar graphs and interested in the least coloring of planar graphs. But this kind of restricted, this kind of S4 colorable is kind of variation of least coloring. So this is a natural question. We say a subset S of S4 is good if every planar graph is S4 colorable. And then the question is which subset of S4 are good. The four color theorem says that this is good, identity is good, right? Because every planar graph is 4 colorable. identity. If this is S for colorable is the same thing as for colorable. And there was a conjecture of Masayawa, husband of Korea, which says that every planar graph is signed for colorable. This conjecture is equivalent to say that this is good, and the Kine and Stephen conjectured every planar graph is signed Z for colorable, and which means that this is good. But both conjecture are disproved. Okay, so let's look at the picture. So this picture shows the family of subsets of S4. So each point here is a subset of S4. Okay, this is S4. These are the singletons. Okay, empty set is not included. Okay, then which of these sets are good? The singletons are good subsets. This is the identity is good, that is for color theorem. The other singletons are good, that is trivial, that's for some trivial reasons. Okay, so how about the others? So if so we know that this is bad. So this 9 is good and this is bad. This 9 is good is basically for color theorem, and this S4 is bad is something like non-fortrucible. They are planar graphs non-fortrucible implies this. Okay, so it follows from the definition that if S is subset of S prime and S prime is good, then S is good. So there's a boundary here, so which says on the left-hand side are the good subsets and the right-hand side are the bad subsets. Then the problem is, where is the boundary? Is it very close to this 9 or close to this side? Okay, so how tight is the four color theorem, and how tight is the result that S4 is bad? Okay, so the conjecture was mentioned before that implies there's some rooms to strengthen four color theorem. So you have some little bit of room here, but those two conjectures are disproved. Okay, so we have introduced the 5 concepts that are refinement of least current of graphs. We only discussed planar graphs here, but all the least current concepts are interesting for general graphs. Actually, they are more interesting for general graphs. Okay. We mentioned many questions, particular questions when we define the concepts, and most of them are open, but we do have some partial results. Okay. For example, we asked, is it true that every planar graph has matching M such that G minus M is fortrucible? And this turns out to be true. And then the next question is true that every planar graph has an induced matching M such that G minus M is fortrucible. This turns out to be false. Okay, the answer is no. And say what are things between? We may propose this conjecture. It's open. The conjecture says that every planar graph G has a matching M such that G minus M is fortrucible, and this matching induces a 2-degenerate subgraph of G. Okay, this conjecture is open. Okay, so for the second concept, we asked what is the smallest epsilon such that every planar graph is 4 plus epsilon trucible. Okay. And the current norm, upper bound, and lower bound are as follows. So epsilon is less or equal to 1/2, and greater or equal to 1/63. The lower bound follows from a early result, Mazaka-Hanning, and the upper bound was proved by Gruchuk and myself. And for the third concept, let us go to multiple current. And we asked what is the infimum of those epsilon such that every planar graph is AB trucible for every AB greater or equal to 4 plus epsilon. Okay, and of course this infimum of those epsilon is unknown, but we have The answer for this one is no, and this we don't know. And for this one, we have a bound that epsilon is greater or equal to 2 over 9. Right? So this is the best null bound we know. We don't know any non-trivial upper bound. The trivial upper bound is that epsilon equals 1, because if this is greater or equal to 5, then we know that is AB choosable. But say, for example, it would be interesting if one can prove that epsilon is less or equal to 0.9. And this null bound was proved by myself. The fourth refinement is about the restricted list assignment, as we said, for planar graphs. And we have, this is four-color theorem, and this is non-choosable theorem of void. And how about these three partitions of 4? It turns out the problem is solved. And for this is no, and this is no, and this is no. So they're all no. Okay, so this no was proved by Choi and Quine, and I also proved it, but later I didn't know their results and proved it independently. And then this no was proved by Camelis and Foyt. And this no is the strongest one. This no implies this no and implies this no. Okay, because this is a refinement of both 2, 2 and 1, 3. Okay, so if there is a planar graph which is not 1, 1, 2 choosable, then that planar graph is also not 2, 2 choosable, and that planar graph is also not 1, 3 choosable. Okay, then the fifth refinement is restricted deep-decaying. We asked about the following questions: which subset of S4 are good? So we know that identity is good, and they have conjectured that these are good. As I said before, both conjecture are disproved, and this is bad, and this is also bad. Okay, this is also bad. How about others? How about other subsets of S4? Okay, and this is also something which this result implies that this set is bad. Okay, this set is bad, and we proved, Jin, Huan, and myself proved that if S contains identity, then S is bad unless S equals identity. So this means four-color theorem is really tight. Okay, you put any more element into S, it becomes bad. Now, how about those subsets S of S4 that does not contain ID? In that case, S is bad unless S is contained in this subset. For this subset, we don't know. Of course, this is to we say S is contained in this subset is up to conjugation, because you can change names of the colors. That does not change the problem. Okay, so this is the picture. Where's the boundary? The boundary is here. Okay, so it's very tight for color theorem. Okay, that's the end of this talk. Thank you.